I'm subscribed, by the way.
All right, guys, so here's the big idea. The big idea is that a force times a time is an impulse. It's what we call the change in momentum. So when you find the impulse, that is the change in momentum. It's how much the momentum will change. So if the impulse is 5 Newton seconds, it means that the momentum is going to change 5 kilogram meters per second. So whatever it was before, it'll be that much more. Okay? So that's the big idea. Now, so far, and I think this is your toolbox, right? So far, we've been applying the impulse momentum theorem to a single object, like a golf ball. A club applies a force. The force is 300 newtons. It lasts 0.007 seconds. What's the final velocity of the golf ball, right? We've been solving those kinds of problems. We've been applying this to an object. So what we're going to do now is broaden our focus a little bit and apply it to what we call a system. So a little bit of vocabulary. If I have an entity whose size is irrelevant to me, it acts as a single object, I call it an object. So we call this an object. I don't really care whether it's 10 centimeters or 5 centimeters. I pretend like all the mass is at the middle, and I call that an object. And that's an object. But when I'm studying systems, we call the two of them together a system, so that's a collection of objects. All right, so that's just how we use the words. Object means one thing whose size is irrelevant. We can treat it as if it's a point. A system is a collection of objects that somehow interact. All right? So what we are going to do is we're going to apply this impulse momentum theorem to a system, not just one object. Okay? So that's kind of the next step we're looking at. So in the top diagram, we've got an arrow flying along. It embeds in a little cart, and the cart and the arrow move off. Okay? This is a system. We're calling the cart and the arrow a system. Now, if you look at just the arrow, is there a force on the arrow during the collision?
No. What?
Yes or no? Is there a force on the arrow during the collision?
No.
Go ahead, everybody's got to vote. Yes or no?
No. No.
So, does the arrow change speed?
Yes.
It definitely slows down. And a change in speed is an acceleration. And what causes acceleration?
Force.
So there must be a force if it changes speed. So is there a force on the arrow during the collision?
Yes.
Yeah. The car is pushing back on it. Now, is there a force on the car?
Yes.
It's sitting still, and now it's moving. There must have been a force on it. So there's forces involved in the collision. But here's the point I want to make. Are any of those forces that are involved in that collision, are they external to the system, or are they internal? Are they inside? Are they forces inside the system, or outside acting on the system? Inside. They're inside. They're internal forces. Okay. So in this collision right here, there are no external forces. There's definitely forces, but they're internal. And if there's no external forces, there's no impulse on the system. Okay, that's the idea. Look at the bottom one here. I've got two cars. They're sitting together, or they will be. There they are. An explosion or a spring pushes them apart, and they go flying in opposite directions. Were there any external forces on this system?
I don't.
The cars pushed on each other, but those are internal forces. There's nobody on the outside messing with this, shoving it. Okay? There's maybe a spring in there that was compressed and it detonated, or an explosion or something. But that's an internal force. So again, in this system down here, there are no external forces. So here's what we can learn from that. If there's no external force on a system, then the impulse on the system is 0. Okay? So the system is the two cars together. If the impulse on a system is 0, then the momentum of the system cannot change. because the big idea is that the impulse equals the change in momentum. If there's no impulse, no external forces on a system, the momentum of the system cannot change. Okay? And if the momentum of a system cannot change, then whatever it starts with has got to equal what it ends with. Right? The temperature doesn't change. It means the starting temperature and the ending temperature were the same, right? If the momentum doesn't change, then whatever you started with is what you end with. So all of that we can write mathematically with symbols like this. If the external force on a system is 0, then the change in momentum is 0, which implies that the final momentum equals the initial momentum. Okay? So that's kind of the theory, where we're coming from mathematically. So we're going to take a look at different kinds of collisions. So a couple of kinds of collisions. I don't have a super ball, but if I had a super ball, you just have to sort of imagine here. If I had a super ball and I dropped it and it bounced, how high would it bounce?
What's a Super Bowl? Halfway.
A super ball, super duper elastic.
Oh, more
Ball.
than halfway.
Yeah, if I had a super ball and I dropped it, it would bounce all the way back up to where I started. Okay? It would be a completely, perfectly elastic collision and it wouldn't lose any energy. No energy would be lost. Right now, this guy loses energy because it only comes up this high. It lost some energy, right? It lost it during the collision. So I can't demonstrate a super ball because I don't have one, and they don't really exist. But in one kind of collision, an elastic collision, kinetic energy is conserved. And we can set up elastic collisions, just not between a ball and the ground. Okay? So elastic means energy is conserved. What would happen if you had a collision where energy is not conserved? What would you call that? If elastic means energy is conserved, what would energy not being conserved be called? Inelastic. Yeah, use the in prefix from Latin, right? It means to negate. So inelastic, you know what I'm talking about? You can describe something, or it's indescribable, not describable, right? In is the Latin prefix, which means to negate. So inelastic means energy is not conserved. All right? So that's most collisions. When I drop a ball, it doesn't bounce as high as it came from. Some energy was lost in the collision. That's inelastic. You hit a tennis ball, you hit a golf ball, you throw a basketball and it rebounds. In almost all collisions involving our sort of normal everyday things, energy is lost. Okay? So they're inelastic. There's a special case of inelastic, and that's called completely inelastic. And that's when things hit and stick. So like if you have a wad of Play-Doh and you drop it, how high will it bounce?
A little bit.
Tiny bit. Okay, but if I take it out of the bag, it'll A, get dirty. There's a lot of hair on the floor. And B, it'll just go thud and stick. That's elastic. I mean, that's completely inelastic, excuse me. So, those are our 3 collision types. We'll come back to them, hang on. So, here's what we did in lab. You guys actually set up inelastic and elastic collisions in lab. When we had the Velcro between the cars moved along, they smacked and they stuck together. That's completely inelastic, they didn't stick. And what you noticed, I think, was that the momentum of the system, the momentum of the teal car plus the momentum of the gray car before the collision, when you added that up, you got the same thing as after the collision. The difference between these two was pretty small. And if it was not less than 5%, you're supposed to do it again. Right? So we found that for our system, the 2 cars together, although one car slowed down and the other car sped up, the total momentum was about the same before and after the collision. Okay? But energy, not so much. We had a lot of energy before, we lost a lot, almost half. So we would call this an inelastic collision. Energy was not conserved. The energy before and after was not the same or even close. So we lost energy, but they were hit and stick, and the momentum was about the same. That was true for the first 4 trials. In each case, the momentum before and after was very, very close. It's not exactly the same because of our experimental uncertainty. We will never get the exact result perfectly because our equipment, there's all kinds of little bits of error here and there and stuff. But it's pretty close. When we switch to the magnets, guess what kind of collision that is?
Magnetic.
It's elastic. Nothing deformed. The two objects bounced off each other, and you should have found that not only was the momentum pretty close to the same before and after, but so was the energy. The changes in the energy for the magnets were very small. They're very close. We lost almost no energy when those things collided on the magnetic ends. So elastic collisions usually happen when you have things like magnets or electric forces or forces at a distance. Gravity is an example also. So here's a summary, kind of putting together what we know and what we got in lab. Elastic collisions are generally rare, at least in our everyday lives. And when they do happen, they involve things like electricity or magnetism, or possibly gravity, not in you falling to the ground, but like gravity interacting between two objects. So in space, when an object passes by another object and interacts with it, energy is conserved. It's elastic. Okay? Generally, elastic collisions are one in which there's no deformation at all. So you guys remember the high-speed video of the tennis ball hitting the tennis racket and how the ball squished? The ball deformed. Anytime a ball deforms or anything deforms, you're going to lose energy. Okay? Deformation is like friction. It's guaranteed to rob you energy. So the only time things are elastic is when there's no deformation at all, no squishing. And so two steel balls are a pretty good approximation of an elastic collision. So let me kind of, you guys have been playing with this all year long.
Oh.
This is an example of an elastic collision. I gotta bring it up front because the video is on. So what we have here are steel balls, and they do not deform. They're very stiff. And so the energy you have doesn't really go away very fast. That's why it lasts so long. You're losing very, very little energy each collision. If we made one of these out of tennis balls, it would go like 3 or 4 times and stop. Okay? So this thing's kind of fun. It's called Newton's Cradle, and it's an example of elastic collisions. You can actually pull 2 of these over, and 2 go back and forth. Or you can get 3, and 3 go back and forth.
It's like magic.
Or you can do 4. It's kind of fun. Can I leave this here and not bother you guys? So,
You can put it right here.
elastic collisions occur when there's no deformation. There's no squishing, bending of materials. That is pretty rare in our everyday lives. We don't drive cars that are involved in elastic collisions.
Why not?
So inelastic collisions are the normal everyday collisions we experience, and completely inelastic are a special case when things hit and stick. This happens often enough. So for example, if 2 things hit and stick with Velcro, or if you shoot a bullet into a piece of wood, the bullet gets embedded in the wood, and they're stuck together as they move to get off, right? Those are completely inelastic collisions. Here's the big idea. You might want to jot this down in your toolbox. Elastic collisions, energy is conserved and momentum is conserved. Inelastic collisions, energy is not conserved, but momentum is. So when is momentum conserved? Always. Get that away from there.
It's a system.
It's a distraction.
It's not distracting
He hasn't written anything in his toolbox. That's one thing.
Can
Laura doesn't even have her toolbox out, and you're telling her to get away from you.
I'm not worried about her.
Yeah.
So,
Where is it?
you guys ready for the test question?
No.
I'm going to ask you a couple different ways, but one of the ways I'm going to ask you is, in what kind of collision is momentum conserved?
Oh!
All collisions. Okay? In what kind of collision is energy conserved?
Elastic.
Elastic. And in what kind of collisions is energy not conserved?
Inelastic.
Inelastic. So if we don't know whether energy is conserved or not, does it matter? Can we still use momentum?
Yes.
Those are 2 questions, sorry there.
Oh.
It does not matter. Yes, we can still use momentum. We can always use momentum in collisions, whether energy is conserved or not. And that's why physicists study momentum. Okay? Because we can apply the principle of momentum conservation whether or not energy is conserved. All right, so I'm going to solve 3 examples. One slowly and in detail, and then the other 2 I'm just going to kind of flash up there and just point them out. And then you're going to solve some problems, okay? So, here's my first example. You got a girl standing on a skateboard holding a pumpkin. She's going to chuck the pumpkin that way. What happens to her?
I don't think that's
She's going to go that way.
okay.
What's not realistic?
He used all of his examples from his kids.
What's not realistic about that?
Definitely not.
It's fall. There's pumpkins laying all over everybody's yards. You don't have a skateboard?
Don't you play a pumpkin skateboard?
All right, anyway, moving on. So guys, we're gonna make a diagram. So there's an interaction here. The girl shoves on the pumpkin. That's an interaction between the girl and the pumpkin, okay? Before the interaction, they're both standing still. After the interaction, the girl is moving which way?
Left.
To the left, and the pumpkin's moving to the
Right.
Right. It will help you to make arrows showing the direction of the velocities. Okay? So, 22 years of experience tells me that people who make sloppy diagrams spend lots of extra time on their problems because they miss simple little things that they shouldn't have. Okay? One of which is the directions of the velocities. If you get the direction of the velocity wrong, you'll waste lots of time. So just make a diagram, carefully sketch which way things are moving. All right, now the variable list. We've got momentum, so we need mass and velocity. So we are going to have an external force, maybe or maybe not. Turns out to be 0 in this case. We've got the mass of the girl and the mass of the pumpkin. We've got the velocity of the girl and the velocity of the pumpkin before and after the interaction. So, since we have 2 masses, I've got to use subscripts to differentiate them, right?
Yep.
I'm going to use G for girl and P for pumpkin. Okay? So they make sense, so I don't get confused. So, this is the velocity of the pumpkin before she throws it, the velocity of the pumpkin final, after she throws it. The velocity of the girl before she throws the pumpkin, the velocity of the girl after she throws the pumpkin. You see how I'm using subscripts?
Yes.
Okay, so the external force is 0. We're assuming that there's nothing outside acting on them. They are a system, the girl and the pumpkin, despite how unrealistic it seems to Aubrey. The mass of the girl, the mass of the pumpkin are listed in the problem. What is the velocity of the pumpkin initially before she chucks it?
0.
It's 0. How do you know?
Because.
It's stationary.
Yeah,
It's
it's
immobile.
stationary.
She throws it.
Okay. What's the final velocity of the pumpkin?
6. 4.
It's 4. And it's positive. It's to the right. The velocity of the girl initial is 0 because she's holding the pumpkin and standing on the skateboard. And we are trying to find the final velocity of the girl. Okay? All right. So here's how it goes. We start with the big idea. We are going to apply the impulse momentum theorem. All right? So that's this. We are going to apply it, though, to the system, not the pumpkin. If we just looked at the pumpkin, there's definitely an external force on it, right? The girl's pushing on it. Its momentum will change. So we are looking at the system. So since there is no external force on our system, that goes away. And I get that the change in momentum is 0. See, you tracking with me here?
Yes.
If the change in momentum is 0, it means the final and the initial are the same. The difference is 0, so they're the same. Okay? This means the difference. All right. If they're the same, I now need to write an expression for the final momentum. Momentum is mass times velocity. So I've got to take the mass of the pumpkin times the velocity of the pumpkin final, plus the mass of the girl times the velocity of the girl final. That's the final momentum. And that's got to equal the mass times the velocity of each thing before she throws it. So it's going to look like this. It's a little long, but you guys will be okay. It's the mass of the girl times the velocity of the girl final plus the mass of the pumpkin times the velocity of the pumpkin final. That's the final momentum. That's got to equal whatever we start with. Now, we got some things that are 0 to make our life easy. Oh, by the way, what are we going to do with this? What are we solving for? Albert? Yeah, we're trying to solve for the velocity of the girl final, which is right there. So, that's 0, and that's 0, because the initial velocities were 0. So if I rewrite it, this thing equals 0. I'm trying to find the velocity of the girl final, so I'm going to bring this to the other side, so now it's negative. Divide both sides by the mass of the girl, and there's my expression. Plug in my numbers. Can you guys do this in your head?
No.
Yes, do it. No calculators.
It's 0.8. It's 0.8. Negative
Isaac,
0.8.
put that calculator down.
Negative.
Throw it away.
Yes, Nick.
Negative 0.8.
Negative 0.8
How do you do
meters
that?
per second. Hey, what's 10 times 4?
40.
40 divided by 50?
I don't know.
80 divided by 100? 4/5?
Oh.
All right. Okay, does this answer make sense?
Yes.
So first of all, does the negative make sense?
Yes.
Yes, because we know the girl is moving to the left. Now, the pumpkin was thrown in 4 meters per second to the right. Does it make sense that the girl is moving 0.8 to the left?
Yes.
Because she has a much smaller, Nick,
Distraction.
because she has a much smaller mass. I'm sorry, because the pumpkin has a smaller mass, it'll be going faster. The girl has a bigger mass, she'll be going slower. Okay? All right, does that all make sense? I've saved it for you, but I mean,
Sure.
if you weren't here today and you just looked at that, you'd be like, holy macaroni, what do we do today in class? All right, let's solve another one. Slightly different. One tiny difference. In this case, this is what we did in lab. I've got a teal car moving down the track. It smacks into a stationary gray car. They stick together and they move off. Okay? So, what is the same? What two things are the same? Is it? Yeah, the one that before is an equal amount after. Yeah. That's true. Oh, nothing. Okay, so here's what's the same. If they are stuck together, that means their final velocities are the same. You don't need a separate final velocity for the teal car and for the gray car, because they're stuck together. So I am not going to have two different final velocities. I'm just going to have one final velocity. See that?
Yes.
So, there's my variable list. The gray car, the teal car, and the gray car is initially stationary. The teal car is initially moving to the right. So see here's my before, here's my after. I'm going to apply the big idea, because the hit and stick, the final velocity is the same. The big idea says that a force times the time is a change in momentum. The force is 0, so the change in momentum is 0. So P final equals P initial. The blue is just my commentary here, in case you are looking at this later. So, what is the final momentum? It's the mass of the teal car times the final velocity, plus the mass of the gray car times the final velocity. That's the final momentum. That's got to equal the initial momentum, which is the mass of the teal car times the initial velocity of the teal car, plus the mass of the gray car times the initial velocity of the gray car. But the gray car was sitting still initially, so that goes away. I'm going to solve this mess for the final velocity. Which final velocity?
The bone.
They're the same.
Yeah.
They're stuck together. All right, so that goes away. I'm trying to find the final velocity. Both of these have a v final in it, so I factor it out. If I factor it out, I get teal and mass of the gray. If you're not sure if that's right or not, distribute. Distribute is the opposite of factoring, right? That times that gives you that. That times that gives you that. So that's right. Now, divide both sides by this sum to get the final velocity. So you get the mass of the teal times the velocity of teal initial divided by the sum of the masses. Plug in your numbers. Can you do that in your head?
No.
Yeah, me either. It's 0.325. Okay? Now, does that answer make sense? Callie?
Sure.
Why?
They're moving to the right.
So it's positive. That makes sense because they're moving to the right. What about the 0.325? Wouldn't you expect a higher number?
Yes.
No, because momentum is conservative.
Still on you, Callie.
They're going slower than the blue and
Yeah, this one was going 0.55, and you would expect if it smacks into something else, it would slow it down, right? So the number makes sense. It's less than 0.55, and it's still positive. Okay? All right, so when you guys solve problems, make a diagram before and after. Make one little diagram of before, and make another diagram after. Make sure you use arrows on the diagram to indicate the velocity. Make sure you get the direction for the velocity right. Choose subscripts that are meaningful. Some people call it M1 and M2. And then they switch and they get it all reversed and they can't get it right and they don't know what the heck's going on. And half an hour later, they erase it all and start over. Okay? Just choose interesting subscripts that make sense in the context of the problem. If you've got a girl and a pumpkin, use G and P. If you've got a bullet and a block, you're in trouble. Well, maybe the block is made out of wood. You could use B for bullet and W for wood, right? Just, you're going to get confused with subscripts, so just make it as easy on yourself as you can. Okay? I've seen people use capital B and little b, and then they forget which one was which, and they switch them, and it's a big mess.
You just said B for bullet instead of B for boy.
If you have a bullet and a block.
Oh, I thought you said a boy for a hot second. I was like, wait,
No.
that's wrong.
All right, last hint. Guys, these problems are not hard, but they are tedious. And a lot of you have trouble working through a long calculation without making silly mistakes. So, just slow down and be careful. It is almost always to your advantage to work slower and get it right the first time than to work fast and take 5 shots at it before you get it. Okay? So, work slowly. Okay, last example. I've got a basketball moving to the right. It collides with a tennis ball that is moving to the left. After the collision, the basketball is moving to the right. So it looks like this. Agree?
Yeah.
Before, the basketball is moving to the right, tennis ball is moving to the left. After the collision, the basketball is moving to the right.
How does that work?
I'm going to use B for basketball and T for the tennis ball, surprisingly. I do not know the final velocity of the tennis ball, but they are not stuck together. So I've got to keep track of the final velocities. I've got the final velocity of the basketball and the final velocity of the tennis ball separate. I'm going to do the exact same thing I've been doing, guys. The force times the time is the change in the momentum, and there's no external force. The two balls just collide. That means the final momentum is the initial momentum. The final momentum is the mass times the velocity of the basketball, and the mass times the velocity of the tennis ball. The initial momentum is the mass times the velocity of the basketball, and the mass times the velocity of the tennis ball, initially. Okay? So, this is the big old equation you get. You're going to solve it for the tennis ball's final velocity. That is right there. So, bring this term to the other side, make it negative, and then divide everything by the mass of the tennis ball to get the velocity of the tennis ball final by itself. Okay? So you get this mess. Guys, close your computers there. So, when you solve it, you'll get a big ugly expression. Work through it carefully. Now, here's an answer you may not expect. Okay? 18 meters per second seems kind of big, right? This is the exact same thing that I did last week with the ball. I can't do it sideways, okay? But if I could throw the ball sideways and you throw the ball this way and it hits, the tennis ball would bounce back, okay? But watch what happens when I do it vertically. I'm going to bounce the ball, and it's going to hit the ground, and it's going to be coming up when the tennis ball is coming down, because I'm going to leave a gap between them, okay? So watch what happens. Oh. The tennis ball really takes off, doesn't it? It flies off of there. Same thing would happen if we could do it sideways. I would love to have somebody throw the ball at the basketball this way, and I throw it that way, and it hits here, and it flies off at 100 miles an hour that way. But it's just too hard to organize and get right, and it hits the side and goes crazy, so we're not going to try that. But it turns out that the basketball loses a little bit of momentum, and the tennis ball gains that momentum. But because the tennis ball is so light, it goes a lot faster. And you guys remember the tracks, the cars when you had a really heavy one with the magnets, and you bumped into the other one, and the other one went flying, right? It's the same idea. A transfer of momentum happens, but if something is really light, it's got to be moving really, really fast. Okay? All right, we've got 10 minutes. I want you guys to solve the first problem in the homework. Grab your computer, do the very first problem, see if you can get it done before you forget it. Just go meeting. I don't care.